All right. We'll be going through the question papers where we got most of question papers from just analytical chemistry, and we'll be able to answer them one by one. Okay. So that is it. So now what we need to understand is that let me go through the first question. Okay. So I'll be much of explaining than just lighting, because lighting will take time and it's a paper, so it's a big these questions, they are more of essay, so it's important that we just get points. All right. So it says chromatograph is a well-established analytical procedure. Okay, this is true. It's a well-established analytical procedure. Let me just increase my pen size. All right. So, which is continuously evolving with new modified procedure showing great promise. All right. So, give an educative description of chromatography, explaining how it works as a technique of qualitative data and quantitative analysis, or just the qualitative and so what we need to understand is that, first of all, chromatography is an analytical procedure or separation used to separate component of mixture based on their different interaction between the stationary phase and the mobile phase. So chromatography is an analytical procedure. Okay, analytical procedure, right? This is an analytical procedure or separation. Okay, so this is an analytical separation technique. Okay, so it's a technique used, so it will be used to separate components of a mixture. So used to separate components in a mixture, or of a mixture, right? But this separation should be done based on the different interaction different interaction between the mobile phase and the stationary phase, because this is what will enable actually the separation to occur. It's when the other parts actually hold the other molecules or solute between the two solution, or between the two media. Okay, that's if these two, there is no difference in interaction, meaning that everything can come the way we dipped it, the way we put it. So that's how it can come. Okay, so it's a different interaction between, okay, like I said, between the mobile phase and the stationary phase. So the interaction of solute or components between these two medium will enable actually how fast they'll come out, how slow they'll come out. By that, different component, because has different solubility and also different volatility, or just the velocity. Okay, so and the mobile phase there, I've already written the mobile phase. Okay, so that's what actually will make the separation to occur. So what I'm trying to say is, imagine a race between, let's say, molecules. Okay, between molecules, the molecules, they have to reach there, that point. There's something that push them to move along that, and inside this test tube there is what we call a dry thing. Okay, and that's what we call a mobile phase. So the mobile phase will enable also to allow molecules to stick to it, or just to continue moving with the stationary, I mean with the mobile phase. The stationary phase is what is sticked to the walls. Okay. So imagine molecules are racing. These are molecules racing now in this. Then some molecules will move very fast to reach that end, and others will move very slow to reach that end. So why does this occur? It's because they interact different with the stationary phase. So this stationary phase is very important because some they will be influenced to stick, and hence they take time to come out or to elute fast on that. As a result, that will enable us the interaction. So that's what we mean when you say um, um, chromatography. That's actually what is happening. That's how we use the procedure. So now let me go through with you to say the most important component under this are: one, we need to know the stationary phase. What is this stationary phase? The phase that stay fixed to the walls of the medium or the column, our heart of chromatography, which is the column. So we have the column there. There are different type of columns. So the stationary phase is what stick to the wall. Okay, what is stick to the wall? Sometimes it can be liquid, and that will enable us different forms of chromatography. If it's liquid, it's liquid chromatography. Solid is a liquid. So all these, they actually forms different forms of chromatography. So this, what is sticked here most, it can be solid or liquid. Most we use liquids, like even in gas chromatography, we use liquids, okay, as the mobile phase. No, in gas we use gas as the mobile phase. But there are other things like under the capillary tube, okay, we use liquid as the mobile phase. Okay. Then the mobile phase is that move. It can be liquid or gas. Okay. So there's no mobile phase that we'll put as a solid. Or the mobile phase, we want something that can move through this solid to the wall or liquid to the wall. Okay. Then the analyte is a substance that actually uh, that is being analyzed. That's what we call the analyte. It's the one that is pushed by the mobile phase. Okay, the mobile simply means moving. Then the column is what we call, this is where, this is our heart or separation or carry in this column. Okay, okay. Then the detector detect what actually has been formed, the peaks. Okay, so now how were these peaks coming out? Also other aspect of how they are broad and small will also be involved as another way of separating them. Okay, so we have actually different types of them. I'm just giving this information in case. Different type of chromatography, and one of them is gas chromatography, GC. So under this, the mobile phase is the gas. That's what we need to understand. So it uses volatile compound that can evaporate. So the other type of chromatograph, it's a liquid chromatograph, where it uses the liquid as the mobile phase. Okay. So it uses liquid as the mobile phase. The other type of chromatograph is the thin layer chromatograph. This one, it uses the liquid as well. I think we have been performing this thin layer chromatography. This one also use the liquid. I think this is one of the one we use in schools. Okay. Then the other one is paper chromatography. So paper chromatography, it also use you also use liquid. So it's only gas I think that uses liquid. All right. So this one, the paper chromatography, is the one we used in secondary, remember, where example of solute we use dyes. Yeah, this one, yeah, if I'm not mistaken. So that is it. Now coming back to our question, which says work as, how can it work as a technique of qualitative and um, a technique of qualitative and quantitative analysis. So let me say one or two things here about what is important to note while this actually is being performed. Okay, so what do we do this then? Um, imagine, imagine for us to get, we know qualitative data is the data that we can just see by our eyes. Then Quantitative is about how much amount of something we make. Okay, how do we analyze that amount? That's what we call qualitative. Okay, so qualitative will be when this procedure is done and we identify what compounds are present. So we identify, okay, we identify compounds present, and that is what we call um, qualitative. Okay, so once we are able to tell that this is a compound, we have identified that identification, but coming now to how much we have identified, that is quantitative. So identifying compound, that is qualitative analysis. So identifying compound present, that is qualitative analysis. Okay, then to determine how much of each compound is present, that is the quantitative analysis. How much each compound, each of those we have identified components or compounds. So how much compounds is present, that is the quantitative. Now we are talking about now the calculation, quantitative analysis. Okay, so identifying how much compound present. Actually, that imagine example. Let me give an example of what I'm trying to talk about. Suppose in a mixer, like a chromatograph will separate, let's say perfume. That what makes perfume. The perfume that is not made up of water. There are a lot of things present there. So in perfume, we can separate one, the alcohols, that thing that makes it to dry fast. Okay. So let's say alcohol. Alcohol is also found there. And also we have that fragrance, which is the esters. Okay, esters. So the esters, we have also the aldehydes. Okay, the aldehydes. Okay, so if these all are collected, all right, this means that each appears as separate peaks on the chromatogram. So once they are detected by the chromatogram, so we'll find peaks on the chromatogram as happen like this, again this. So that now identification of these peaks, as stating that there are peaks there of alcohol, peaks of esters, peaks of aldehyde. This means that we are now doing the qualitative analysis. Okay, then how much of the aldehyde present there, that is the quantitative. All right, so those are the things, just the educative information I can give. So let's see the other things that we can terms. Okay, the first term that we have is what we call retention time. What is retention time? This is the time taken for a compound to travel from the column to the detector, or time taken from the time of injection to the time of detector appearing on the detector. That's what we call retention time. So it's given by the TR there, meaning retention time. All right, so that is it. And the other thing that I can talk about under detention time, it's the formula will be actually given as, so suppose this is a peak. Okay, this is how they have moved. Like this is there will be what you call a void time, that time of not detection. Then there they start detecting. Now let's say this is, they happen to be detected at this point. So this means that there's a time there. Okay, this is the peak, let's say. There's a time there that's at the injection, so we'll call that one as TM. Okay. Then from there, then there is what we call now the retention time, from the time of injection to the time of detector where the peak has been detected. So that's what we call TR, the retention time. So the retention time is the time taken for a compound to travel through this column to the detector, or the time taken from the time of injection to the detector. That's what we call a retention time. So it's calculated as retention time, the difference in here there. All right, retention time, it's also called, by the way, if they are to use the other word, is also called um um retention time. In fact, yeah, no, it's just called by R like this. Okay, all right, so that is it. That's what you can, that's how you can calculate the retention time, time taken from the time of injection to the time of detector. That's what we call um retention time. Or you can define it to say this retention time, um you can define it to say this retention time is a time between the sample injection and the analyte peaks reaching the detector. So the detector will give the peaks, of course. So that time taken is what we call the retention time. So let's now talk about, so that is it about retention time. Let's talk about the void time. What is this void time? Of course, I know it's not familiar. The term is not familiar, but it's also important that we talk about it. So before I even talk about the void time, suppose that I want you to get a clear picture of the retention time. Um, Suppose we have, let's say, methanol, okay? Methanol, which is traveling, let's say the detection time for it to be detected to give peaks on the chromatogram is taking 2 minutes, okay? Then let me talk of ethanol again. Let's say this one is taking 4 minutes, okay? Then let's talk about now if propane, let's say propanol. Okay, propanol, let's say is taking 7 minutes to form for it to appear on the chromatogram or for it to give peaks. So that's what we call its retention time. So the longer the retention time we have, the stronger the interaction, because it shows that it took time in the chromatograph there. Okay, so that is it about retention time. Hope we have gotten something there. So like the propanol, it means that it has big interaction, and there's where we'll bring the aspect of, let's say, the mass resistance, all those things under AD um, equation. Okay, so that is it about. Now let's talk about void time. So what is this void time? When you say void time or T0, okay, uh, is the time taken by an returned compound to pass through the column. So there will be, I think this is what I can call a void time. The time taken, all right, the time taken by unretained compounds, okay, by unretained compound to pass through the column. So this compound from here to there is not like retained, it's not given. So what I'm trying to say is a void time is a time taken by unretained compound. So unretained, all right, let me rub that, unretained compounds to pass through the column. So that unretained compound to pass through the column is what we call the void time. So a void time, time taken for an retained or by an retained compound to pass through the column. Okay, by time taken by an retained compounds to pass through to pass through the what? The column. Okay, that's what we call void time. It represents a mobile phase travel time in short. And retained is the what? The mobile phase. So in short, it represents a mobile phase travel time. So unretained something is a mobile phase because we are not interested in the analyte. So the time taken by that is what we call the void time. So it represents, I mean, it represents it represent the it represent the mobile phase, because unretained compound, the time taken for it actually to be displayed on the chromatogram. So that is it. All right, so that's what you can say about the void time. Yes, so that will be the time taken for an retained compound to pass through the column. So the it represent the also called the mobile phase, the guy which travel. We are not interested, it's just there to help us. Uh, just there to help us retrieve those things. That's all. I mean, push those things. Then the other thing that we'll talk about is what we call the A factor, or just the A, okay? The alpha in short. So this one is called S. By the way, before I even talk about, let me give a clear picture on the void time. Imagine air in a gas, all right? Air in a gas, all right? In a gas chromatography, okay? That air that actually also is influenced or traveled with the mobile phase, which is the selected gas, such as, let's say, the nitrogen. We have also the use of All right. So we have also other gas carriers such as the nitrogen. We have also other gas carriers such as what the helium. Okay. So all these two. So now, how do we now handle that? So the air can also be contained in these gases. All right. So you have to be very careful. Okay. That is it. So imagine air now in a gas chromatography. That air that actually comes with the air, you are not interested in the air, so that is actually the time that air actually takes is what we call the voyage time. Okay, it represents the mobile phase travel time. In short, it's not retained. So time taken by a compound, by an retained compound, to pass through the column. So that column, we have to be very careful with the way we bring the columns, the type of gas flows we use, stuff like that. So it's very important as well. All right. So that is it. So let's talk about the resolution now. The selective factor. So when you say selective, selectivity, just selectivity. Okay. This selectivity, it actually represents, it will measure how well two compounds can separate. And uh, yes, it will measure how well two compounds can be separated. It's given as alpha, okay, is equal to the whatever two compounds has is the biggest, okay, let's say by mass. It's the biggest, okay, by factor, which factor. So say, let's say that is B, then over A there. So we want always this to be greater than 1, okay. So it will tell us how well two compounds can separate by this ratio, okay. So we need it at least uh when we want something big here, okay. So when we have in the range of 1 to 5, that actually gives us a best or faster separation, because sample with the low k, not really k, um the samples with the biggest number, then it should be on top, so that we can have at least the range of 1 and above there, and that will be the best separation. Okay, so that is it about selectivity. It's just the measure of how well two substances or compound can be separated. So this is, let me light it. We are saying this selectivity, it's about um it's a measure of how well, how well, okay, how well two compounds are separated. So it's a measure of how well two compounds are separated, okay. By that, using that formula we gave there, the alpha is given as, at least we need to be greater than. So you always bring, so sometimes they can ask you to calculate that. Make sure that you put a value that is bigger on top. That's all. So the K1, so I can also write it to say, okay, alpha is given as the K2, okay, over K1. That's what I can simplify. Then this K1 is a compound factor of, is a factor of, and these factors we rent them the factors, the equilibrium factor, we rent about the k. Anyway, that's none of my business, but just know the formula to say it's given as this. All right, so the condition is that the better separation will occur when this one increases from 1, let's say, to 5, like I demonstrated there. 1 to 5, when a is greater than 1 or equal to 1 to 5, then that actually gives a better separation, like I said, 1 to 5. Okay, so that is it about let's talk about now the resolution. Okay, what is resolution? Resolution describe how well two peaks can be separated or are separated. So about, okay, this is about this one is talks about how two compound can be separated, right? How to how two or well compounds, how two compounds can be separated. It's about the selectivity. How do we select? Okay, how can they like we have two, but um how can we separate, how well two compound can be separated is the A factor. Then the other S factor, which is resolution, is about how well two peaks are separated. Okay, this is about how well two peaks are separated. All right, that is it about this guy resolution. It's about, we have two things that are close like that. If we are to bring them on a chromatogram, in fact, this one measure about how effective is that chromatograph. How do we able to see? Suppose they are here, but when you display them on the chromatograph, they are telling you that they are separated like this, but they are attached to each other. Okay. So here the resolution is poor, here the resolution is active. Okay. So that's what we get when we say the resolution. Okay, let's talk about now the column efficiency. So there's also column efficiency. Again, they have mentioned something like highest equivalent to theoretical plate. So that's what it means, that one. So they have also like, or so we'll define what a column efficiency. Column efficiency, but before that, um I said resolution is about how two peaks can be differentiated or separated, right? Or the base, how the broad, the compound that are very close. It's about how two close substances can be separated. That's what we call resolution. So resolution of an instrument matters as well as you are doing this chromatography. So retention time, it's about the time that actually takes to take. Then there's also peak width. Okay, so resolution will give us the retention time, how the time taken for them to be displayed there, and also the peak. So the peaks, how well we're able to see. So this resolution depends on the peaks for it to be active, and also um, depends on uh, the retention time. So that's where the resolution actually depends, because the retention time is about the time taken for them to appear on the chromatograph. So this means that resolution, when we have, let me just see, I just want to give more details about the resolution because it's important than just defining and I leave it. Okay, so resolution is about when we have, let's say, resolution which is RS is equals to, let's say, 1. Okay, so this means that there's poor separation. Okay, so good separation is when achieved when we have a resolution of let's say greater than 2, in short. Then when you have a resolution of, let's say, is equals to 5 or 1.5, this is when we have this, we have a baseline separation. So baseline separation. Baseline separation. So the base now are separated when we reach the, but when we reach that resolution is equals to 2 or greater than 2. So this means that this is the excellent separation. So very important about this. So that is it. Okay. For selective factor, selectivity, we have to actually look at 1 to 5, then we'll have a good separation. So that is it. Let me talk about what we call column efficiency. So resolution depends on the peaks and also the retention time. This resolution, the best resolution we can have is when you have 1, that is poor, 1.5, that is base separation. When you have more than 2, that is the excellent separation or excellent resolution to say. Okay, that is it. So let's talk about it. So the column efficiency, which is the last one here. So column efficiency measures how well a column separates. Is the ability of column to separate the compounds. Okay. So column efficiency measures, or this one is about, so when I say about, it means measures. Measure, it's about how well, all right, a column separates compounds. Okay, so it's about how well a column can separate, the ability of a column to separate compounds. That's what we call column efficiency, represented by N like that. Okay, so and this column efficiency, let me do this. Let me, okay. So that is it about column efficiency. So column efficiency will depend on the number of theoretical plates for it to be effective. The more theoretical plates, the more plates that are in that column, the more, the better the separation. So it depends on the theoretical plates, and also it depends on the retention time. Retention time also, that's where the what? The resolution depends. So retention time is actually a very important thing, because that's the time taken for us to see the peaks or the chromatogram or the data displayed on the TV or detector. So the other thing that we need is the width of the peaks. So how well it will actually, this is in association with the RS, the resolution. Why? The peaks of width, all right, the peaks width. Why? Because the width of these peaks actually matters with the efficiency of the column efficiency. So the peaks are differentiated by the baseline when the resolution is 1.5. So also the ability of a column to separate the two compounds depends on the baseline as well. So the peaks width also matters. So a higher number of it, in short, higher number of plates gives actually better separation. Okay. The increase in the number of of plates, we get better separation. That is it. So that's what we can say about that. Then they have added the information of height equivalent to theoretical plates. So this one, it's just the calculation of this height equivalent to theoretical plates is actually given as should be L over the same H. I don't know if I'm not mistaken, but this should be the formula, whereby the length of the column, then the height of the length of the breadth. I have forgotten, but this should be the formula. Then yes, the L simply means the column length. Yes, the breadth or the column length. All right, the column length. Then the height. Uh, so we need to have a big column length as well, so that the separation can happen. So we need a smaller h so that we can have better efficiency. So, and this is where efficiency is about how possible within what you have to do the work at the right time. That's what we call efficiency. Okay, that is it. Let's go to some other aspect. Okay, I'll be very fast here. Okay, so it is often found that by controlling the capacity K, okay, capacity factor, this capacity factor, I'll talk about it. Okay, separation can be capacity factor, which is also the called the retention factor. Okay, so capacity factor is also called the retention factor. Separation can be greatly improved in chromatograph. So by controlling this, separation can be greatly improved in chromatograph separation. This can be achieved by changing the temperature in gas chromatograph or the composition of the mobile phase in liquid chromatography. All right, what are they trying to say here? Okay, this means that um all right, so now let's go to the question. Explain how temperature, composition of the mobile phase also can influence the separation of the mixture in different substances. So if the temperature, so in gas chromatography, GC, all right, temperature affect the volatility of substances. So this affect the volatility in gas chromatography. So it affects temperature affect the volatility, okay, the volatility of the substances. Okay, so what do I mean? The volatile, like how much are they able to, like, to diffuse, or to, because as a temperature result, how much are they able to actually turn into gas so that they can move with the gas. So if temperature increase, compound vaporize very fast, compound vaporize fast, okay, and again the retention time will decrease because they will reach fast to the detector. So RT or TR decrease. Okay. Then the other thing is the peaks elute fast. Okay. The peaks that we need to see, they elute fast. They go out easily. So peaks elute fast as a result of increase in temperature. But what we need to know is that too high temperature can also cause poor, too much high temperature can cause poor separation. So we need to be very careful in as much as we apply temperature so that to speed the process. But again, it causes us to do more many separation because the temperature is high. Okay. But again, it can also bring those problems. Okay. So that is it, the temperature. Because let's say in a liquid chromatograph, mobile phase composition affect the solute solubility. Okay. So the mobile phase composition also. So we talk about this also. So composition of the mobile phase, how can it influence separation of mixture? So example, changing the ratio of, let's say, methanol to water will affect the separation. Let me give a scenario. Like let's say we have a benzene, taurine, or xylene. Like if temperature is increased, all compound will elute fast, but separation will reduce. Why? So the composition of these two of mobile phase also matters. Okay, the composition of the mobile phase also matters because the mobile phase composition will affect the solute solubility. Okay, so if the mobile phase so in short, the mobile phase ratio also the composition matters. So we need, like, it will affect the separation. Like I said, suppose we have, let's say, benzene and toluene. If the temperature increase, all compound will elute fast. So the composition of also this matters because if temperature is to be increased, they might elute fast. So we need at least the composition that whereby the other compound or composed in that analyte is actually somehow robust to temperature, and that will help us. Okay, so that is it about the distribution or the composition of the mobile phase, because when temperature is increased, the two guys can be affected, and hence we need to pay attention to the composition of the mobile phase or the mobile phase that we have made, especially the liquid mobile phase in a liquid chromatography. So those things like thin layer chromatography, paper chromatography, it uses the liquid phase or mobile phase as the liquid. So that is it about these two guys. So it affects the temperature, has affected the faster, and the peaks will erode fast, but also the same increase in temperature can also cause the damage or the poor separation, and also the volatility of compounds temperature affect that. All right. So let's talk about now. I need to be very fast. So distribution of coefficient or distributive or distribution coefficient K, okay, is an important quantity in understanding the movement of analyte through the chromatograph. Write down a mathematical expression showing the relationship, okay, between K and the concentration. So this is where we get the equilibrium concentration. So the concentration is that we need to have the stationary phase over the mobile phase. So the K is given as the composition or concentration of the stationary phase over the composition um, or concentration of the mobile phase. So where this S I said is the concentration in stationary phase, then this one is the concentration in immobile phase. If these two equilibrium have, I mean these two guys have equal equilibrium or concentration, then we have K is equals to 1. And when K is equals to 1, this means that the everything is at equilibrium. Okay. So that's the data that, so this is affected by 1. Okay. Write down the expression showing the relationship between K and concentration. So we have written this. So identify factors affecting this. So factors affecting this, we can talk of temperature. We just identify temperature is one of the cause for every aspect. The other one you can talk of is, let's say, the nature of stationary phase or the composition of the station. No, yes, the composition of stationary phase. What if it's um affinity chromatography? So whereby the other compound also have been put there to attract the analyte composition. So I can talk of the nature of stationary phase. So nature of stationary phase, they will affect the, even the nature of also stationary mobile phase also can affect. Okay. What if they interact more to the mobile phase? You find that it will affect the equilibrium. So the other one we can talk of is also molecular structure, especially under affinity or adsorption chromatography. So we can also talk about molecular structure, about the forces that are contained within the structure. They can be intra, stuff like that. Then we can also talk about the pressure also. The pressure and temperature are two important parameters that we need to take in consideration while performing this chromatograph type. So those are the things. We can also talk about the polarity of the mobile phase, how polar it is. Okay. So if, anyway, that is it. Then the importance of, explain the importance of K in chromatography. So the importance of K in chromatography are, one, it will be there to determine, because the interaction in this equilibrium for it to be set, it affects the what? The retention time. So determine, because we are here in this chromatograph to talk about retention time. Okay. We are there to measure the retention time. Those are the data we like code after the procedure. The other thing is separation efficiency. Okay. Was the separation efficiency or effective? So those are the things you have at the end. So you look at those parameters. Separation efficiency. Okay. Then the other thing is it will influence the capacity factor. Okay. What is the capacity factor? Is the same K I'm talking about. All right. So the same K, which is called the capacity factor, it will be affected by these guys. All right. So that is it. So the K sometimes is called the distributive coefficient or partition coefficients. This means that how much they are distributed. So we talk about the capacity factor. So determine the retention time, separation efficiency, are the important. I explain the importance of K in chromatography. One, it will be there to to control the separation efficiency. Okay, and also influence the capacity factor. Okay, influence. All right, that is it. So let's say if a compound prefers stationary phase, okay, they are moving within this column. So there's an equilibrium at the mid, then there's a stationary phase, there's a mobile phase there. So if a compound prefers stationary phase, they will stick to this. So meaning that the stationary, we remember we said stationary phase, meaning that the K will be very high. Okay. When K is high, then the retention time also increase. Okay. So we increase there. That is it. Then we have, that is it about the 3 marks there. Let me concentrate to the 3 marks. To obtain high resolution, the 3 factors, by the way, resolution depends on these 3 factors. So resolution, we have the efficiency, the selectivity, which is the A alpha, and we have the retention itself. Okay. So it depends on this retention time and also the peaks. Okay. So factor affecting resolution, we have one, the column efficiency, which is that, and also selectivity, which is the A factor, and also the retention time. I mean the equilibrium. Okay. Okay. So from there, then it's even given the formula there. Explain steps that can be taken in each of the 3 factors to optimize their contribution in order to obtain higher resolution. So we can talk of, first of all, let me talk about the efficiency, okay, which is represented by N, okay, column efficiency in short. So column efficiency, it's about, when we explain this, so the question is explain steps that can be taken in each of the factor. So one, I said this one is the N, column efficiency. This column efficiency, the resolution is depending on what? On 3 factors. One, resolution depends on the 3 factors. One, the column efficiency, all right, which is the number of plates. Then we have also the selectivity. Then we have also the K factor. Okay, so that's what we call a K factor. So how do you find this then? Or the retention factor, to say. This is the retention factor. Okay. Then from there, these are the things we have there. Okay. So we said where N is the efficiency, which is how much the column perform. Then A is the selectivity, which is A, about separation ability, how well 2 substances can be separated. Then retention factor K, which is about this retention factor K, it's about analyte interaction. How much are they interacting, the analytes? All right. So now to explain how we can improve each one, improving N, okay, use longer columns. So we need to use longer column there. Okay, use longer column. So smaller particle sizes. So the particle should be, or in as much as you have a longer column, then use small particles or small particle size. Then the other thing that we need to do is we need also to have better packing. The way we pack these ones, we need to be very careful. So we need to have a better packing. So that is it. Then how can we improve the selectivity, which is the A factor, or the A factor? So this one we need to change because it's about talking about how well 2 substances can be separated. So we need to change stationary phase if it has those compositions that actually stationary phase change, stationary phase to be changed. So you change that, and also the other thing is you also adjust the temperature, because the temperature will allow these guys to separate the two. Then The other thing is change solvent polarity. Okay, that is it. That's how we can improve. Then how can we improve the retention K? This one. So this one can be improved by adjusting the mobile phase composition. So mobile phase composition, okay. Then also modify the temperature and change the pH if possible, especially in liquid chromatograph. pH also should be adjusted. Okay, that is it. Okay. An important goal in chromatography is to achieve sharp, symmetrical peaks, yes, as this optimize the chance of analyte separation and improve detection. Unfortunately, one challenge that a chromatographer meets in learning chromatographs is peak broadening when the peaks are actually interacting. List the three sources of peak broadening as identified in the late theory and summarized in Van Dan equation. Okay, so the first thing is, by the way, the formula is given as um let me write H as in the damped equation. H is given as diffusion plus the longitudinal over the average velocity plus the same average velocity of this solute, then times this C, which is the mass resistance transfer. Then we said this A is the air diffusion, then B is the longitudinal diffusion, then C is the mobile phase, I mean the mass transfer. Okay. Then U is the mobile phase velocity. So velocity of the mobile phase. So that's what is there in the AD equation. So we want to list the three source of peak broadening as identified. So we have identified one is the air diffusion, B is the longitudinal diffusion, C is the mass resistance or mass transfer to say. Okay, that is it. Those are the three things, but I can break them down. So let me start with the air diffusion. So this air diffusion, it is caused when different molecules take different paths. Okay, so it's about two molecules taking different paths like that. That is air diffusion. Okay, so as a result, peaks they can spread. Okay, then when we talk about the B factor, which is the longitudinal diffusion, the B longitudinal diffusion, this one is talking about how molecules diffuse from high concentration to low concentration. So it's about how they can diffuse from here, given there are a lot of them, how much they can diffuse to the low concentration. That is the longitudinal diffusion. So occur mainly when in gas chromatograph as a result that interaction of gases, they can spread out. Then the other parameter is the C. So the C, which is the mass transfer resistance, it slows the transfer between the stationary phase and the mobile phase. So it's about the resistance. So the more the resistance, the more the mobile phase velocity. Okay, it favors the mobile phase velocity because of this C there. So it can affect the C. So as a result, it will cause also peaks broadening. So this is the equation that actually wanted you to, and I've talked about them. That is it. Okay, we are still there. Okay, one model that assists in understanding the column efficiency is the Pratt theory. Explain the assumption of this model, Pratt theory. How it assists in explaining column efficiency. So the more the plate we have in a chromatographic column, it also matters with the column efficiency. So we need to have a lot of these. So the higher the n, the better the separation. So plate theory, okay, explain the assumption of this model or the theory and how it assists in explaining the column efficiency. Okay, so plate theory assumes that the column contains main equilibrium. Okay, these equilibrium plates or stages. Okay, that's what it assumes. It assumes to say the column contains main equilibrium stages or plates. Okay, so each stage is called theoretical plates. Okay, theoretical. So it assumes that the column contains, that's what, like, the guys, they are just trying to say what brings about the separation is about because of these columns or the plates. That's where the other molecules stick there in those plates. So that's what these guys, the scientists, thought of actually to say it's just an assumption, it's not real. All right, let me just pause a bit. Okay, so it's about how these guys, I mean, the columns can be separated. I mean, the column can give data. Okay, so that is it about the column theory or the plate theory. That's the assumption. The assumption is that plates, I mean, the columns contain many equilibrium plates. The stages or the same plates that we talk about them are what we call theoretical plates. So they are even written there, theoretical plates. So it states that it assumes that the column contains many equilibrium stage. So it assumes that the column contains many equilibrium stage, contains many equilibrium stages. And these stages, each stage is called theoretical plate. So each stage, all right, so that is it. So those, they were assumptions. So we said assumptions were column consists of main plates, equilibrium occur in each plates, equilibrium plates, and also solute partition between phases. It will actually occur. How the partition is about the distribution. Those were um, so the goal is when we have more plates, okay, more plates, then the better separation. Okay, good or better separation. That is it. That is it about this. That's what you can explain there. Let's go. So the following data were obtained for 4 compounds separated on 20 meters capillary column. All right, it was a good column. All right. So the first question is, calculate the number of theoretical plates for each compound and the average number of theoretical plates for the column. So what we do is, we use the formula. All right, we use the formula. All right, so the formula is calculate the number of theoretical plates, which is the n. So say n is given as, okay, 16 times the retention time tr, all right, which is the then TR over W, then squared like that. So I'll demonstrate for the first one. So we have 16 there. Calculate the theoretical for each. Okay, so let me get for A. So we have 16. The TR there is what? 8.4 over the W which is the minutes width, that is in short 0.15. Okay, so that punch times 2. I don't have a calculator with me, but you find the answer. You do the same, you do the same. And the average number of theoretical plates for the column. So what you do is, after finding all the theoretical plates that you find for the 4, then divide by what? By 3, because there are 3 of them there. Okay, then you find the average. Then calculate the average height of the theoretical plate. So how do you calculate the average height? So we calculate the average height, which is h is equals to the L, the width, then over. All right. So how do you know the width now? Okay. So calculate the average height of theoretical plates. So the average height is given as um, uh, how do you find the average height? Okay, suppose you have calculated now for this one, and also you have calculated everything. So you calculate the average theoretical plates. You also calculate the average height, because this is the um, average, what's this? Calculate the average height of a theoretical plate. So what we do is we apply the formula. We say, okay, height equivalent to plates, which is this one, we say it's given as number of theoretical plates there. So that is these values. So you add them and also divide by the average of this, and you'll be able to find the height there. So the average of these two, that will be your length, then divide by the number of n. Okay, so you'll be able to find the average height. Okay, so where L is the column length, and the column length is given by that W. All right, so that is it. Then explain why is it possible for each compound to have different number of theoretical plates. So the reason is that why each compound have different theoretical plates. It's because different diffusion rate. It's as a result of different the other compound will have different diffusion rate, and also will have a different interaction. That's the reason. Different interaction will result in uh, different theoretical plates. Okay, and also different retention time. Okay, so different retention time will result in different theoretical plates. Like, what influence the theoretical plates are the retention time and also diffusion rate, also just the interaction. Okay, that is it. So let's look at differentiate between mechanism between adsorption and partition. Okay, so what's the difference between partition and the adsorption in this uh, chromatography? So one thing that I can assure you is that first you can come up with a table like that. Okay, so there I can write, let's say, adsorption. Adsorption, this one depends on the interaction of solids to the mobile phase especially. So by that, it will bring that. Then partition is about how particles are distributed. The partition is about distribution. So adsorption, in terms of the stationary phase, adsorption, it uses the solid. Okay, then the partition about distributing, this one it uses the liquid. Then the other thing that I can talk of is that the mechanism used here is about the attraction. Okay, surface attraction. because they will adsorb to the surface, to the solid surface. Then here, the mechanism used is about the solubility, how they distribute, solubility distribution. Okay, that's how I can differentiate distribution. Okay, then example, or let me just say the interaction here, it's about bonding, surface bonding. Okay, then here it's about liquid to liquid distribution. So we'll use, because the mobile phase is the liquid, so liquid to liquid distribution. Here it's about bond surface distribution, or just the bond itself. So by the way, this for adsorption, it uses what we call a silica gel. That's the silica gel. That's what it uses as a mobile phase, which attract the molecule, to trap the molecules. Okay, that is it. Then the partition compound will just dissolve between two liquids, like they will dissolve between two, and they will result into different partition, meaning the distributive. Okay, so that is it about it. Do we have more questions? No, I think this marks the end. Thank you very much. We have talked one or two things, at least you can now recall. Though it was a very long video, but at least you have one or two ideas. So this marks the end. This is the end.